Okay, it's 1 minute past. I think what we'll do is go ahead and get started. We can circle back with anyone who joins a little bit late. But in any case, welcome everyone to the first ever public training class for OLI Flowsheet Modeling Basics. I am your host, Jordan Pierce. I work in sales at OLI. I've been with OLI for about a year. I think what we'll do is we'll get started with an introduction, an overview of OLI, and then we'll jump into the training. So I'll just orient you a little bit to OLI for those of you who are new. If you are not speaking, would you please mute yourself so that we can have a clean recording? Again, these recordings will be available after the class when they're fully rendered. So we have two classes, two sessions. The first one today. So again, welcome everyone. Thank you very much. And then one on Wednesday at the same time this week. So I'm going to go ahead and jump into it real quick. So we'll do a very quick introduction of who's on the phone from the OLI side. It may be a little bit hard to tell us apart. We're all listed as OLI systems host, except for, I think, Dira. She may be in and out. But in any case, OLI systems today, we're having me help host the introduction and then field any questions and make sure we take breaks and all that kind of stuff. Diana Miller, PhD, is leading the class today, so she'll be doing the bulk of the discussion. She's a corrosion engineer and has been with OLI for a few years now. And we also have Dira Silvera on the line, who is our academic lead and training coordinator, and Ezekiel Vicente, who's another one of our application engineers, similar to Diana. A little bit of a different focus. But since we're expecting quite a few people today on the training, we want to make sure we have enough resources to address any questions and so on. So a quick introduction to OLI. Many of you already know who we are and what our solutions can do. But today I want to focus on the flow sheet and our OLI flow sheet simulations for aqueous streams. So this is going to be mainly focused on this tool. Dan is going to give you a lot of background, but I do want to sort of orient you. So OLI has been around for almost 50 years now. We have started our 50th year. So we have been focused throughout our history on the physical property modeling of electrolyte systems. So this is water systems. This is any kind of system you can think of just about where you have electrolytes are dominant, that have interesting phase behavior, and our primary focus is the thermodynamic and thermophysical calculations around streams that contain water and electrolytes. So been around for a long time, can consume OLI in a number of different ways. We have a lot of interesting folks on our team. We have some of our application engineers on the line, as we mentioned, as well. We also have a team who are not on the line today of about 8 thermophysical property modeling experts. So we do spend a lot of time making sure we get that chemistry right. A very quick breakdown of our software solutions in case you are not familiar. So the sort of core product is up here in the top left, is OLI Studios, a stream analyzer. This is essentially a virtual laboratory on your desktop. So I mentioned our focus on electrolyte thermodynamics. This is a place where you can create streams and you can run surveys and understand the phase behavior and do pH calculations, surveys across the different pressure range, pH range, temperature range, and so on. So this is really kind of our core product, and many of you may already be familiar with it. We're not going to touch on it today, but we do have a corrosion analyzer that builds on a lot of that same thermodynamic properties to calculate your corrosion rates and understand your repassivation potentials, things like this. But again, today, our focus is going to be on OLI flow sheet. So this is essentially taking those calculations and those sort of single point calculations you do in Stream Analyzer and bringing those into a flow sheet environment to understand your system, to understand how unit operations are going to affect various separations in your plant, different kinds of calculations. So we'll get into those in a little bit more detail in the training. We also have products that we call our alliance engines. So this is taking the same thermodynamic engine that powers each one of these individual products and leveraging that thermodynamic database inside of a third-party process simulator. So this is like Aspen Plus, HYSYS, Pro2, et cetera. We recently released an alliance engines for KBC PetroSim. So we're not going to touch on those today. We're mainly focused on OLI flowsheet. A quick background, and Diana's going to cover this in a little bit more detail, but I want to make sure you're aware of the different frameworks that are available inside of OLI. Excuse me, the AQ framework is our legacy framework. This is where water is dominant, kind of requires up to 70% or so of water. This is our legacy equation of state, our thermodynamic framework. For most of the calculations that we do, we would recommend using MSC. This is really the sort of state of the science of electrolyte thermodynamic calculations. Again, your particular application will help you decide where what framework you need, and Diana will cover that in a little bit more detail. But this is an equation of state based on the Helgeson equation of state. It's we've got about over 6,000 species in the data bank that can be used inside the frameworks across 80 plus elements. So Diana, again, will cover this in a little bit more detail. But today we're focusing on our process flow sheet calculations. So we're not going to touch too much on the water chemistry analysis or the corrosion side or the automated custom applications, but I do want you to be aware of those as you're looking at these examples and you're looking to understand what your process is and how it's going to be used by not just an R&D group or an engineering group, but even possibly into operations. So again, today's focus is on our process flow sheet calculations. A few more things I want to mention. This is an equilibrium-based model. So keep that in mind also as we're looking at these calculations. So when we're looking at, we're calculating phase equilibrium across solid, liquid, vapor, and organic phases. And keep that in mind. This is not a dynamic environment. We're assuming equilibrium, and it will have an impact on some of the calculations. This is not too far different from most flow sheet applications or many thermodynamic calculations, but I think it's worth bearing in mind. As we move into these calculations for flow sheet, some of these advanced properties will become very important and are calculated by our thermodynamic engine. The transport properties, osmotic pressure, again, a lot of these things will be driven and used inside of flow sheet. Again, I just want to make a quick mention of corrosion simulation. If you have any interest, you can please just let us know. We can talk about this either offline and in a separate conversation. We do run through a cycle of these public web trainings. So while today's is focused on flow sheet, we have one coming up that's just on the basics of electrolyte modeling. We have one that we focus on the use of scale chem. And then we also have one that talks about the basics of using our corrosion, doing corrosion simulation inside of OLI Studio. There's a lot of real solution Poiret diagrams that many customers find useful for their particular application, calculating localized corrosion, these kinds of things. But again, today we're focusing on OLI flow sheet. I want to leave this up here just for a minute. So as you're thinking about your particular application, if you already have some experience using flow sheet, you'll be familiar with some of these things. But if you've not used OLI flow sheet before, please look at some of these chemistries, think about the unit operations that you want to cover, and then think about also what you want to get out of a model, because it's going to be important, not just creating the model and running the model, but the interpretation of results will be particularly important. So again, we're just taking a lot of the same calculations that we do inside of the thermodynamic engine that runs all of our solutions from Studio to Flowsheet to the Alliance engines, and we're putting all those together in a Flowsheet tool that allows you to do combine rigorous chemistry simulation, the complicated thermodynamics of aqueous and electrolyte solutions, and then putting that together with the Flowsheet blocks so you can get a decent understanding of your process. I always like to show this slide as well, so it gives you an idea of some of the different types of applications that OLI has helped simulate and helped model. and to basically understand the properties of the systems, understand how to optimize it, understand what impacts the different operating parameters, and basically KPIs in your process. So not all of these are going to be relevant to each of you that's on this phone call right now, on this training, but do keep in mind as you look at your particular applications, there are a lot of templates that we do have available to help you get started. Lastly, as I mentioned, results are very important in understanding what they mean to your process and to your system. So as we go through this training, we're going to try and give you a little bit more of an idea of what's happening in this black box, in this software black box. So Diana's going to spend a lot of time talking about how to set things up, sort of these inputs here, deciding what you want to analyze and creating a process schematic inside of the flow sheet, but then understand what's happening under the hood so that when you do get output, you get results, you'll understand what they mean and what the limitations are and all those good things, because again, you want to understand what's happening under the hood so that you can make the right decisions around your process, around your recommendations for changes and so on. This is all I had today. What I do want to remind you is that there are a number of people on the phone call, and normally we would do an introduction. I think we might be taking up too much time if we did that, but I see many folks on the line. As you have questions, please feel free to either raise your hand or send a chat in the chat window. So we were talking earlier, WebEx has changed things a little bit, but hopefully you'll be able to navigate your way around. So again, this is Jordan Pierce, and I will be keeping an eye both on time and on questions that come through the chat. So with that, I will stop sharing and I will hand it over to Diana, and we can get started with the class.
Thank you, Jordan. That was really good introduction. Now, let me know if you see my screen, okay?
Looks good. I see it now.
Great. Okay. Good morning or good afternoon or good evening, depending upon your location today. Thank you so much for being here in this first OLI Flowsheet ESP training course. As we go through this training, please let me know if you want me to go a little bit faster or slower when I am going through the cases, just because I don't know. At the moment, I just don't know who has been a user previously of OLI Flowsheet or who is new. So just let me know if I'm going too fast or too slow so that I can adjust my velocity as I teach this class. So thank you so much for your time today. Today, I'm going to basically show all the basics of this Flowsheet tool. How to enter streams, how to enter inflows, ionic inflows, how to set up unit operations, how to set up sensitivity analysis, all of these features that we have in the software. And I want to empower you with all of these tools so that you can perform all your simulations without no problem. For the ones that may be wondering what the ESP stands for, I have been asked this question several times, so I just wanted to start with that. The ESP, the OLI Flowsheet ESP, the ESP stands for Electrolyte Simulation Program. So that's the first thing that we're learning today about the naming of our software. Just for a quick disclaimer, I will be using version 10 of the software. So if you have a slightly different or an older version of the software, let's say version 9.6 or 9.5, you will probably obtain different results. And also, if you have a version that is 9.5, let's say, so we will not be able to use the MSC SRK framework. But it's okay because we are not going to use it for the examples, but I just want to make sure that there will be some differences if we have a slightly different versions of the software. And as Jordan was mentioning, we will be recording this class, so you just have it as a future content available for you whenever you want to revisit some topics of today. These are the course objectives. And really my main goal for you is, that you become familiar with the software, learn how to navigate it. I will be showing you all the capabilities of the software, as I said before, so you feel empowered to create your own simulations, and also that you learn how to interpret the results that the software provides to you. So as Jordan mentioned, the training will be divided into sessions, and each session will be less than an hour. So we will be, I will be doing presentations for around 53 to 55 minutes, and then we will take a quick break. Let me just put the pointer here. A quick break from 5 to 7 minutes. I would usually prefer, if it would be ideal, if you have two monitors, where in one monitor you have the presentation I have for today, and in the other one you have your screen. But if that's not possible, then I would recommend that you split your monitor, so then you can follow along with the instructions I will be giving today. So you can always split your screen, use the Windows key and the left or right key in your keyboard, and that will help you to divide your screen. For the materials, you should have received the manuals for this course, and I will just walk through some of those chapters. I will just show the essence of some of those chapters, and we will be also giving to you this recording. Please let us know if for some reason today you are not having access to the software. Please double check, just make sure that go to the software, click on it, and that you are having access to the software, because we will be using it a lot today. If it is not installed, let us know, send a chat or let me know, so that Dira or Jordan can help us to provide to you a trial serial number and give it to you right away, so you can install the software and follow along with the training today. Okay, so this is the course agenda. Today we are going to learn all about the user interface, how to define streams in the software, identifying the main unit operations, and we will also learn a procedure that we use in order to build a flowsheet case, introduce manipulators and controllers, recycles, and also set up an absorption column and sensitivity analysis. In day 2, it will be more hands-on regarding examples. I will be doing a reverse osmosis example, a cooling tower example, a crude distillation unit example, and I will touch on some of the reactors, the basics of some of the reactors that we have in our flowsheet tool. Now, if you don't see an application that you would like to see for day 2, let me know, send us a chat, and you say, Diana, could you please show an example of this specific application? If you let me know, I can work on it today or tomorrow, so we can show it in day 2, okay? So I'm just send us an email or a chat so that I am aware of that, and we can prepare that for you for next class. Okay, so just let me know if you're having technical issues. I can help you with that, troubleshoot if you have any technical issues today. Since we are recording, please mute your mobile devices so that we don't have any any sounds in the background. And please feel free to participate. If you want to participate, just raise your hand. Usually, now I don't know if in the new WebEx, you will see the hand next to your name, but probably if it's still there, if you want to raise your hand, let us know, or simply use the chat, or just go ahead and unmute yourself and ask the question. Today, my colleague Ezekiel Vicente will be helping me with the chat. So if you have any questions, he will be helping me to answer any questions that you may have regarding the training. And by the end of the course, once we complete the course, you will be receiving a certificate of completion that you can feel free to share on our LinkedIn profile, just to show that you have successfully completed this course. And you can also join to the OLI simulation group in LinkedIn. These are the links. I will provide these slides to you so you can have access to this. And after the course, of course, if you are doing your simulations and you have any questions, we have several channels that you can reach OLI support. You can go to the web to contact tech support. You can email us. Now, there is a new feature where you can create your own portal with your username. Not your own portal, your own account in our OLI portal. And in there, you can also submit your cases and follow how we're doing with the case, the status, everything. So this is something new that you should probably create your account and check it out. It's brand new. Or simply, you can just call us. This is our phone number for tech support, so just simply call us anytime that you have any questions with your simulations. My rule is if you spend more than 10 minutes trying to figure out why your simulation is not converging, why you're having an issue, is contact support. And these are all the channels that you have to contact us. Okay, so let's get started and let's start talking a little bit about OLI Flowsheet ESP. So OLI Flowsheet ESP, as Jordan mentioned at the beginning, is a steady-state electrolyte process simulator. And it will help you to perform energy, mass, and species balances in your simulation. So you can, the cool thing about being an electrolyte process simulator is that now you can track speciation, the species or the electrolytes throughout the whole process in Flowsheet. And also, we are using all of these underlying physical relationships to calculate those mass balances and speciation balances, etc. So we are using the electrolyte thermodynamics. For this, we are using 3 different thermodynamic frameworks: the AQ framework, the mixed solvent electrolyte or MSE model, and our third framework, which is the newest one, which is the MSE SRK framework. This one is mostly for upstream oil and gas, and we will not be covering this or using this model for the simulations today. So that is one, the electrolyte thermodynamics. We are also using equilibrium relationships and chemical speciation as our underlying physical relationships for all our simulations. And the OLI Flowsheet ESP simulation will help you to predict flow rates, composition, and properties of the streams. And of course, find out what are the operating condition windows for your processes. Within these properties that you can calculate, thermophysical properties such as surface tension, interfacial tension, viscosity, electrical conductivity, diffusivity, osmotic pressure, etc. pH, all of those type of properties, you can have access to those once you do your simulations in Flowsheet. One cool thing about Flowsheet is that you have 2 options to enter your streams. So if you are familiar with Aspen class or HYSYS, you know that you always enter your molecular inputs. But now in Flowsheet, you also have the option of entering, if you have a water analysis, then you can enter your chemistry using ionic inflows. So this is something new, and we will learn how to use this specific tool to enter ionic inflows in Flowsheet. Okay, so let's get started. The first thing that we're going to learn today is all the different parts of the interface of Flowsheet. So we become familiar with it, and then we know exactly where to go or exactly where to find specific functions that we want to do while we're doing our simulations. So the first thing we're going to do is please open, let me just get this. Please open a new file, or not a new file, but open the OLI flowsheet ESP. Let me see if I can bring this. Yeah. So let's go to the OLI flowsheet icon, if you have it, for the version 10, and just double click on it to open the program. Okay. So that will bring, and opening a new window for me, but that will bring this new window here for OLI flowsheet. So simply maximize it here in the upper right corner. So it shows the whole, it uses the whole screen here. And you will see that this screen here, or this new document here, is divided into 6 general panels, and I have some nomenclature here. So those panels are the menu items and toolbars. Here at the top, we have the navigator panel. Here to the left, we have our library down here below the navigator panel. Then we have our flowsheet area, this white area here, where we can create all of or add all of our unit operations, streams, etc. We also have to the right this properties panel that we will use a lot during all of these simulations, and then we will have down here what we call the output window. And we will go through this in more detail. Okay, so the first window that I want to talk about is the navigator panel here to the left. Okay, and for the ones that are familiar with OLI Studio, you know that in the navigator panel you find all of the actions or all of the calculations that you're doing. It's more or less similar here in the flow sheet, and here you will see a tree view of all the unit operations that you're using, the streams that you're creating, the reports that you have created, and also the chemistry models that you're using for this existing document. And as we build the process here in our flow sheet, then you start seeing that if you add a unit operation, then you will start seeing the list of all the units operations that you start adding. And we will see that when we create a process, you will see how this starts to expand. But at the moment in here is everything that you put in your flow sheet or any report, stream, controllers, anything will be shown in this navigator panel. So you can easily have access to them right away here rather than going to the simulation and look for a specific stream. You can just do it here. Okay, that's the navigator panel. The second window that I want to talk about is this library. And in here is where you will find all the unit operations available in OLI Flowsheet ESP. So there is a total of 21 objects in this panel. Okay, 17 of them are unit operations that I have listed here, and 4 of them are control objects. Okay, so we will learn how to use most of these objects that are present here in this library, and also we will learn how to use some of these control objects as well. Okay. That is regarding the library. Then the third window that I want to talk about is the flowsheet area. This white area here is where we are going to build the process diagrams. Let's say, and you don't need to do this, but if you want to, you can just double click here, and in here is where you will start adding your objects and your strings and everything. This flow sheet here, or this white area here, you'll see that it has 3 different windows or 3 different tabs on the top. And the first one is where you create the process. The second tab up here is where you define your chemistry. And the third one here is it will show you the reports of anything that you want to see, okay? But we will explore this flow sheet area a lot, so I will not spend a lot of time here. The other window that I want to talk about is this one to the right. This one is what we call the properties panel. So depending upon what you click on your flow sheet, so let's say you're clicking on this mixer, you will see that the properties panel immediately changes. It's showing now only the properties regarding that mixer. And if we had a stream, and if you select the stream, it will show only the properties for that stream. Now, if you click on any white area, here, for example, in any white area, then it will show you the properties of the entire process. Okay, so in here, you have options such as turn on different optional properties for the whole process. And if you click on this gray button here, long gray button, so you will see that for the whole process, these properties that you see here are not turned on by default because they are expensive to run, so they take longer, and we just turn them off by default. But if you want them on, if you say, let's say you want the rescaling tendencies or the heat capacity, you can simply turn them on for your specific simulation. Okay, but we will go through this in more detail later as we create examples. I just want to show you the capabilities of this properties panel here. And okay, so that is regarding the process or the properties for the process. Let me just bring this slide here. This is what I just showed you. If you want to disable or enable optional properties, then you can do that using the properties panels for the properties panel for the process. Okay, there is one last window that I want to talk about, and it's this output window down here. Okay, this output window really has 4 different subpanels. So you will see down here it has errors. So because I added a mixer here, I have an error or some warning saying that I need to add an inlet stream and an outlet stream. Okay, so it will be warning me what I am missing for the simulation. Okay, so we need to correct these warnings before we run any case, or usually after we run a case, we will also see warnings saying your simulation hasn't converged and this is the reason. Then we have the output. We will also go through that. And here is where we will find detailed information about the calculations. We have the trace tab. It will also give us detailed information about the calculations, but we will need to enable trace in order to see results in this window. And then we have the convergence monitor. And in here, you will always see a graph that will show the progress of, let's say you have a recycle stream, so it will tell you what is the progress for convergence, or if you have a controller, what is the progress for convergence. So that is regarding this, I will call it more like output window down here. Okay, so with that, we have 2 more sections of the software that I want to show. I think they are the most important ones. The first one is this menu tab up here. Okay, we will be using it a lot to define analysis such as sensitivity analysis and water analysis. So that's the menu bar. But the one that we will be using a lot is this tool bar, okay, where we have different functions that we can use while we are running our simulations. So, of course, we will be using the save button. the new button, and if we want to open a new file. So these are no-brainer. We already are familiar with those. But the next one that we will be using a lot is this one. We call it the simulation execution options, okay? So from here, you can run your simulation. You can run it step by step. So it will go, this run button here will run the whole simulation. And this one, the next one to the right, it will be used if you want to run parts of the simulation, okay? In a sequential mode, and parts of the simulation, okay? And we will probably use it. I will see where we can use it so that we can have an idea of what it does. Then you can also pause your simulation. We can stop the simulation, okay? We also have the view section here. You can zoom in, zoom out. You can zoom to fit. We will be using these ones too, so that you get familiar with those. And we will be using a lot these selection tools as well, okay? And in here, we will be able to select anything in the simulation. With this one, for example, we will be able to move our simulation. Then you will have how to add a stream, or the button for adding a stream, to add a energy connection. Oh, this is a control. This is a control signal for controllers, and this is an energy connection. And this one here is for reports. Okay, but we will be using this a lot. Then you'll have here some of these options. Let me just click on select. Some of these options you will be able to rotate, etc. And I think these two here are the most important ones we will be using a lot. Let me just click on this chemistry just to show you, for example, the first one will be I don't know if you can see, I have something on my screen there. So you see here that there is a CF. This is the edits units, or the units manager. And if we click on it, here's where we can change the units for our process. So if you click on customize, you'll see that in here you have moles for input and output variables, but you can always change these units, and we will learn how to do that as we go in the presentation. Then you also have the component name, and this one isn't. I want to highlight this one because some people. Let me just close this and put it in close, and I'll hear something. So this one, it depends how you like to work. If you are more like a formula person, so you will see the names of the components, either NaCl for sodium chloride and H2O for water. But if you don't prefer this formula name, you can always change it to display name. So it will change to water and sodium chloride. My preference is formula. I feel more comfortable with formula, but you always have the choice to change to formula or display name. So I will just leave it in formula for the presentation today, and then click OK. So I will be seeing the formula names for all the components. Okay. Now, one last thing I want to highlight. Let's go back to the flow sheet. Let's say that you lost your library. You accidentally, let me just see what's going on here. Okay. So let's say you accidentally close this library. Okay. You probably click on this X, and that happens. It has happened to me. You just close it and it disappears. And maybe you did the same for the navigator panel, and it just disappears. So what do you do when those things happen, right? Like, how do I make my windows come back? So really, it's very simple. What we're going to do is we go to the menu bar, and we are going to look for the option View. And then we go to Windows and Toolbars and click on my library. This is the one that I just lost. and it comes back, and then View, Windows and Toolbars, Navigator. And it just puts it back to where they belong, okay? Another thing that you can do is, let's say you want a bigger flowsheet area, your process is really big, it's really long, so you don't want this properties panel here. So what you can do is unpin it. So you'll see here there is like a little pin icon. It says auto hide, so you can click on it, and immediately everything goes to the right, gives you more real estate for your process. But if you don't want it to hide, like if you want now that you need it, then let's say you just hover over this property and watch, and it comes back to you. But if you don't want it to do that because maybe it's too annoying for you, so maybe you can just pin it back. Okay, so just click on the pin and it puts it back in place. I will be using the screen that you probably are seeing in when you first open the software, but you can always rearrange how you present all of these windows in your computer, right? You can always move it up. You can always make it smaller. All of those things. But I will keep it like this because probably is how you have it in your screen. So I don't want to cause any confusion there. Okay, so that's the basics. Anything related to the user interface, we should be able to recognize and identify by now. Any questions at the moment? Okay. So we are going to start with our first example for today. It's going to be a basic pH neutralization problem. We will have 3 different unit operations. We will have a mixer, we will have a separator, and we will have a neutralizer. So we are going to learn how to use these 3 different unit operations. And what we are going to do in this example is that we have 2 different streams that are wastes. One is an acid waste, very acidic, contains sulfuric acid and I think chlorhydric acid as well. And then you have a base stream. And we are going to mix them together using this mixer. And then after this mixer, the mixed waste is going to go to a separator. The reason why is because as we mix these two, probably we are releasing some vapor, because if we have a very acidic stream and a very basic stream, probably we are having some heat evolve or some heat, and that will create some vapor. Additionally, we may be forming some solids due to the reactions. Maybe we're precipitating something. So we want to make sure to separate all the vapor and all the solids after that reaction. We are interested to treat the liquid phase only, and it is going to go to a neutralizer. Okay, and this neutralizer will use caustic reagent, sodium hydroxide, to reach a final pH for this neutralized liquid of 9. Okay, so we are going to simulate this specific problem, or simulate this specific pH neutralization example. These are the conditions that we have for the base waste, for the acid waste, and for the caustic reagent. These are my inlets, 1, 2, 3. Okay, so we usually like to teach this procedure when we are doing some simulations, so we never forget what steps to follow after we start creating a process. So this is a procedure that I like to teach. Is the first step is always to set up the units for your example. Okay, then the second step is to define your chemistry. The third step is to build your process. So in here we are going to add our blocks, streams. If you have controllers or manipulators, you also add all of that in here. Then you have a fourth step that is to specify all your streams, your feed compositions. the fifth step is to specify all the specifications for your unit operations. Check for errors, run the simulation. If we have any problems with the simulation, then we will troubleshoot the convergence issues, and then we will analyze the results. So really, if we follow this procedure, it will be easier for us to run a smooth simulation when we are working with Flowsheet ESP. So let's go back to your case, and I am going to delete this. I'm going to simply select it. I could have just selected like this, and I'm going to click delete. So we have a blank canvas here. And the first step is to check the units, okay? So I want to make sure that the units that I am going to use are the default units for this example. So how do we do that? We go to the Units Manager here in Edit Units, click on it, and all of us should see the following information. Everyone should have metric flowing moles. Okay. If for some reason we don't have metric flowing moles, please change it to metric flowing moles. Maybe you were using the first run wizard in your machine, and maybe you changed it to metric flowing mass. Please change it to metric flowing moles, and then click on the Customize button. Okay. Then let's make sure that everything for the inflow variables are moles, and everything for the output variables are moles. Okay. If everything is like this and we're okay, then click on the next tab next to composition, and then go to parameters. And in there, you should see you should have a temperature in degrees C and pressure in atmospheres, and the time in hours. So if everything is like that, then click OK, and we are good. So we have set up the units. We really didn't change anything. I just wanted to make sure that we have the standard units for the simulation. Okay, so we're done with the units. Now the next step is to define the chemistry. Okay, so how do we define the chemistry in our process? So once we're done with units, then you'll see that there is a tab next to Flowsheet, which is the chemistry tab. Okay, you can have access to that chemistry tab either by the navigator panel by clicking on the chemistry tab in there, on the chemistry option there, or simply by going to the chemistry. Okay, here. Now, the procedure of creating your chemistry is as follows. So by default, it comes here to databanks. In here, the software will be asking you, which thermodynamic framework do you want to use? Again, you should have access to 3 different thermodynamic frameworks: the AQ or Aqueous Thermodynamic Framework, the MSC, and the MSC SRK. Okay. So for this example, we are going to leave the default data bank, which is the Aqueous. And in here, you should see the data bank that is selected as the Aqueous. So this is good. There is another option, and it's to add special data banks. How do you add special data banks? You just simply click on this Add button, and these special data banks come with the AQ framework, but they are not turned on by default. And the reason why is because not always you need to have these data banks turned on by default. I have seen some simulations where all of these data banks are on, and really what that causes is a lot of delay in the simulations. So only when you're dealing, for example, with surface complexation, then you turn on that specific thermodynamic frame, that specific data bank. If you are doing ion exchange or if you are this alloy and this corrosion really apply more for the OLI studio, so it doesn't really apply in OLI flow sheet. The geochemical, if you have components that require a long time to form, then you will use the geochemical. But overall, I would not recommend to turn them on by default because it will just delay your simulations unless you definitely need to include one. Okay, so that is regarding the data banks. The second step is to add the inflows. Okay, and we will go back to this inflows tab in a moment. You also have other options here, which is phases. Okay, so if you click on phases, in here you have the option to include or exclude phases. In this case, we don't have an organic phase, so the second liquid phase, that is also the same for organic, is not selected. But the simulation will include a solid phase and vapor phase, and of course, by default, it will include the aqueous phase. If you have a specific component that is changing oxidation state, then you will use the redox option here, and you can include that redox chemistry. So let's say you have iron that is changing flow from +2 to +3. So in here you will select the iron oxidation states to include those equilibrium reactions. And again, and also here you will have kinetics, and here you will add your customized kinetics. By the end of this course, we will learn how to enter or how to modify this kinetics window here. But you also have that option to overwrite equilibrium reactions and enter your own kinetics equation. We don't do kinetics, but if you happen to have the kinetics, you can always enter them here and edit a specific reaction that you may want to overwrite. Okay, so let's go. That is regarding the data banks. Now let's go to inflows. We want to enter the inflows for our simulation. So we are going to enter the following components that you see here. This is a complete list. So that's the list that I want to use. So let's go to inflows. And I'm going to delete this sodium chloride that I had there. It was just for an example, but I don't need it for this chemistry. So I just press the delete button, and that's it. Okay. So we're going to enter 2, 4, 6 different components. The water, it always will go by default. We cannot delete it. This is an electrolyte software, so we will always require water, and it will always go by default. Okay, so then we're going to enter ammonia. So you have different options to enter here. You're going to click in this white area, and ammonia will be NH3. And you'll notice that the software immediately starts to look for those components, right? That's the first one. You can hit enter or press enter, and it will recognize that that's the component you enter. Maybe you don't know the formula, but you know the name. So for example, your next component is going to be carbon dioxide, and it also recognizes the name. You can please press enter. The next one is sulfur dioxide, SO2, enter. HCl, enter. Sulfuric acid. So sulfuric acid. And you'll notice that there are a lot of components that have the sulfuric acid, but the one that appears first is the one that we want to add, and it's the one that the software selects when we press enter. And finally, we have sodium hydroxide, NaOH. Enter. And that's it. That's how we enter our chemistry. These are all the molecules that we need to define to start our simulation. Okay, so I just noticed that it's almost the top of the hour, so I'm going to give around 6 minutes of break, so we can meet at 1 minute after the top of the hour. My time here is 9:56 a.m. So I will meet you at around 10:01. I will put a timer here. I will kind of like this so that it's more understandable when we have to be back. Okay, I'll see you in 6 minutes and I will mute myself. If you have any questions, let me know. I hope those 6 minutes were useful to get some coffee, stretch your legs. If you had any questions, maybe you wanted to ask, let me know. I really don't know how I can tell if people are back. So one way that I like to do is to ask to unmute yourself and say your name and say that you're here, or just raise your hand so I know how many people are back from the break. So if you can just say here.
That's Mike here.
Connie's back.
Good.
Eric's here.
He's back.
Good.
I don't know where the raise hand function has gone, but
I see it. Yeah, I see some hands being raised. Yeah.
I do too. There they are. Excellent. All right, thanks everyone. Yeah, let's go ahead and I think we'll just go ahead and keep going, and folks can just join in whenever they come back.
Yep. Okay, I saw that most people are here, so that's good.
Okay.
So far we have edited units and we have created chemistry. And now we're going to start building our process, okay? So I promise that after this we are going to go much faster. I just want to, as I go, just to highlight the features and talk about where to find things. So you get a better understanding of what things mean within the OLI Flowsheet ESP software. Okay, so the first thing that we're going to do, and what I am going to do, is to really build this process by pieces. Some people prefer to do it all at the same time. Some people prefer to do it piece by piece and identify where errors can happen. So I'm more like the second person. I prefer to do it piece by piece and see where if I have errors and where I can catch them before I run the whole simulation. So that's the approach I am going to take today. So the first step that we are going to do here is we are going to add a mixer, okay? So we go to the library and we have two options. We can either double click or simply click on the mixer, which is this first icon that you see in the library. Just click on it and drag it while you click and put it in your flow sheet. Just release your mouse and now you should be able to have that mixer on your flow sheet. Okay, again, you can double click and it would have done the same thing. If you click down here in your output monitor in the errors, so the software immediately is going to tell you that you need to enter one inlet and one outlet stream in order for this unit operation to run. But we know that for this mixer, we are going to add a basic stream and an acidic stream. So how do we add a stream in the software? So to add a stream in the software, we are going to go up here in the quick toolbar, and we are going to select this icon here that is called Add Stream. And we are going to click on that Add Stream button. Okay, so click on it, and now the selection for the arrow the arrow that you had now has become a cross across on your screen. That cross means that you have enabled that add a stream button. And what you're going to do is you're going to click on the white area of your flow sheet. Just click and then drag the mouse to go towards your mixer. You'll see that the mixer has different red arrows. Those arrows mean you can connect in any of those places. When you are close to one of those red arrows, it will become blue. And that means that you can click again to perform a successful connection. So click, and that should basically have connected your stream S1, in this case, to your mixer. Okay, we're going to do exactly the same, but for our second stream. So we're going to click in the white area. We're going to drag the mouse towards the mixer until we find one of those red arrows. It becomes blue, so that means that now we can click again to make the connection. Okay? And then we need an outlet stream. And the software is smart enough to show you where the outlet goes. So you're going to click, or you're going to go around the mixer, and you're going to make sure that you select, or you go on top of that red arrow, click on it, drag your mouse towards the right, and click again to release the connection there. Okay. Now you have performed, or you have 3 different connections, 2 inputs and 1 outlet. But you continue, you'll see that the cross in your mouse still continues. So if you continue clicking, you will continue also creating some streams. So you don't want that. So what you want to do is just unselect that add a stream button. You can go there to unselect it, or you can simply go to the selection button and click the selection button. Or if you don't want to go go over there, you simply click or press on the escape button on your keyboard, and that should do it as well. Okay. Let me know if you have any questions regarding these connections. So now that we have done the connections, now we need to change the names of these streams. To change the names is really simple. So make sure that you are under the selection mode up here. And now you can click either on the name or on the stream. But in this case, we're going to double click on the name S1. In my case, it's S1. And you're going to double click. And that will create, it will select the entire name S1. And we are going to change that name to, which one will be this one? Let's put it as the base waste. Okay. And now that it's selected, you'll see that the name is selected. I will use my keyboard to move those names. Maybe I want it here. Just for pretty, making it pretty. If you don't want it there, you want it here, it's preferences. You can always put it here to the left or up. It's up to you. Then we have the second stream. We're going to do the same. Actually, I'm going to show you a second way of doing it. And if you click the S2, you can go to the Properties pane to the right, and you go to the General button. And in here, you can change the name. Okay, so you can say, this is my acid waste. Okay, so you can change there, and you can always add notes here. This stream contains sulfuric acid and chlorhydric acid and HCl. Okay, things like that. You can always put reminders here of what you're doing in the simulation. Okay, so that is with the naming for that. I want to put it also here in the, just move it here to the beginning. Good. Then the mixer, I'm not going to change the name of the mixer. I'm going to leave it as mix 1. And for this mix stream, or this stream, I'm going to rename it mix waste. The third way to change the name is to go to the navigator panel, right click on it, rename, and just say mix waste. So those are the three different ways of changing or renaming your streams. Now we are going, the software is still telling us that we have errors, that we need to define the flow of the base waste and the acid waste. It cannot be zero. So we are going to start with our base waste. But we need to know what is the composition, okay? So that's the next step that we're going to do. We're going to enter the composition of our streams, okay? So the first stream I want to select is the base waste. Make sure that you go to the definition tab in the properties panel for the base waste to define the composition, the conditions and composition of your stream. Okay, so now for temperature. So for this stream, we have that the temperature is 40 degrees C. My pressure, or the pressure of this stream, is 1 atmosphere. And in one, I will not change, I will leave this 0 at the moment, just because I want to highlight something later. And then we go to the inflows, okay? So we will enter the inflows. The water content for this stream is 55.51 moles. That's equivalent to 1 kilogram of water. We also have ammonia, 1 mole, okay? Then we have the CO2 content of this stream is 0.1, and the SO2 content is 0.1, okay? So these inflows, of course, come from our chemistry definition. So it just is transferred directly here to our inflow table. And I want you to notice that the total flow of these inflows is exactly the same as the total flow here in the parameter section. So what the software is doing is, here in this green cell, is basically adding all of these inflows components here, and is putting that name, put that total number in here. But let's say that you don't want that this total flow is 56.71. You want that the total flow is 200. So we are going to overwrite that number. And notice that now it's not green anymore because we have overwritten. It's no longer calculated. And the total flow now is 200 moles per hour, okay? But there is a problem here. We are still saying that our inflows, the total amount of that inflows is 56.71 moles. So what the software is going to do is going to do a normalization for your inflows. What it's going to do is going to divide, it's going to get this 200 moles per hour divided by 56.71, and that's going to give you a ratio of around 3.5. And it will multiply this value of 55.51 multiplied by 3.5, the same for this ammonia, the same for CO2, and the same for SO2. So the total flow is 200 moles per hour. So it is a normalization that is taking place there, but the same ratio that you are putting here in your inflows stays the same ratio, okay? That is regarding the base waste. I hope that that makes sense. If you have any question, let me know. I just wanted to highlight that this could be directly calculated, or you can always override the total flow, but that total flow is going to cause some changes in this inflow grid that you see down here. Okay, now let's go to our next stream, which is the acid waste. Click on it. And for this one, we are going to define 25 degrees C, 1 atmosphere. And for the inflows, again, I will show you this. We have 55.51 moles of water. Again, this is 1 kilogram. This is equivalent to 1 kilogram of water. And this is an acidic stream. So we are going to look for HCl. that is 0.1 moles, and we have a sulfuric acid amount of 1 mole per hour. And again, the total flow, the total of the inflows matches the total flow. But in our case, we don't want that the total flow is 56.61. So we're going to override this number with 150 moles. Okay. By this time, it's a good idea that we start saving our simulation. So we're going to go to File, Save As, and I am going to look for a place where I want to keep this. I will keep it here, and I am going to name this example as pH neutralization, and that's it, pH neutralization. And click on Save. Now my name, the name for this file has changed. Okay, so that is regarding the feed compositions. The next step is to define the unit block specifications. Okay, so that is what we're going to do. It's very simple. We are going to click on the mixer. Okay, and for the mixer, we are going to say that this is going to be adiabatic. We're going to leave it like this. An equilibrium calculation is going to be adiabatic, and the pressure specification is going to be the minimum inlet pressure. But I want you to notice that the equilibrium calculation, for the calculation type, it has the adiabatic as an option, but if you click on the drop-down arrow, you have that the mixer has other types of equilibrium calculations. You'll have the isothermal. The isothermal basically is you define the temperature and the pressure, and then it will calculate the properties of the stream at those conditions. Bubble point, it will basically, it depends. Like it can calculate the bubble point temperature or the bubble point pressure, depending upon what you define. If you define temperature, then it will calculate the bubble point pressure. And if you define the bubble point, the pressure, then it will calculate the bubble point temperature. Similarly, it will be for the dew point. So if you define temperature, it will calculate the pressure at which you form your first drop of water. Vapor target. So sometimes maybe you want a specific amount of vapor being formed in your stream. So you will say, out of my 100 moles, I want that 50% of those moles go to the vapor phase. So that is accomplished by using this vapor target. And then you have the isochoric. The isochoric option becomes really handful, really useful when we are doing autoclave experiments, for example, when we have a specific volume and we don't want that volume changes, so that will be our isochoric calculation. But we're going to leave it adiabatic. We're going to calculate the change in temperature. And for the pressure specification, we have by default the minimum inlet temperature. What that means is that it's going to scan these two streams and it will identify the pressure, the minimum pressure. And let's say this is 2 atmospheres and this is 1 atmosphere. So it will select the 1 atmosphere pressure as the pressure specification. But you can always change that to an absolute pressure if you know it, or a pressure drop. Okay. So that is how you set up a mixer. Then we have defined the specifications of this mixer, and I went through these specific definitions for the mixer. And now we have defined the block specification. Now we check for errors. We don't have errors in our case. We saw that we didn't have errors. So now we can go ahead and run the simulation. So again, we don't have any errors. Everything is okay. And we can go ahead and go to the execute button here. You can either click on that button or you can press the F9 key on your keyboard. And just click on the run button and everything is okay. Perfect. Nothing has popped out here with an error message or anything. So we didn't have to troubleshoot convergence issues, so that's okay. And finally, we need to analyze the results. So there are different ways to analyze the results for this partially completed simulation, but I'm going to save these changes just because I don't want to lose any changes I have done so far. So click on the save button, or you can also use the Ctrl+S key to save. And there are different ways to analyze the results, and I will show them as we go. But I want to talk about the most obvious way of analyzing the results in the software, and it's this report tab that you see here next to the chemistry. The report -1 means that it's the first report for this document, and as you add more reports, then they start being named with the 2, 3, 4, 5 number, etc. So let's click on this report tab. And when you click on it, you'll see that you're actually not seeing any type of information here. And the reason is because you need to select the streams that you want to study. So you can either select this drop-down arrow and select the acid waste, for example, or you can simply say or select this add all streams, okay? And it will just identify all the streams that you have in your simulation, and it will bring them all up here. And if you see here, this is a long report, okay? It has a lot of information. And it's very important to understand how you want, what data is really the software providing to you here. Okay, so I will explain some of these tables, and some of the other ones I will just explain as we go. But I just want that you get familiarity with these tables and where to go and how to find information that you want to see. So the first table that you will always see is the stream parameters table. So basically, this is all what we define: temperature and pressure, and moles in our case. However, in here you will also see some calculated information. So you will see pH, hardness, moles true and moles apparent, and then mass and volume. All of these are calculated. And I know that I will get this question: what is the difference between moles true and moles apparent? Okay, so the difference between moles true and moles apparent is that moles apparent will give you the information or the moles in a molecular form, while the moles true will give you all the moles when when you are considering your stream fully speciated. And I will talk about this in a moment with the other tables that we will show, but there are differences. So this is when you consider everything as a molecule. So if you enter sodium hydroxide or sodium chloride as sodium chloride, so then you will be reporting your sodium chloride as sodium chloride. But if you enter sodium chloride and now you see sodium plus and chloride minus, then that will be the true speciation, and that will be those will be the moles that you will be seeing in your simulation. And I'll just explain this in a little bit later in more detail. Then you have the phase flows. This is basically the distribution of your phases, of your moles or mass or volume in the different phases. So we were working in moles, so you will see how many moles go in the aqueous phase, in the solid phase. In solid phase, we don't have any. We have some vapor, and that's it. So again, we have the true versus the apparent. Then we have the phase fractions. Phase fractions is a different way of representing the phases. So you will see that in here you will have 100%. It's going to be aqueous, and then it's going to tell you how much of that percentage is in the vapor phase. So it's basically, it's going to show you in mole fraction or in mass fraction or in volume fraction, the distribution of the phases in your stream. Thermodynamic properties. This is everything that maybe you want to know. You want to know density, enthalpies, osmotic pressure, etc. And if you don't see a specific thermodynamic property that you wanted to see here, probably it's because we needed to turn it on in the process optional properties, and that needs to be calculated if it doesn't show up here. So this is what I was talking about, the true speciated. So in this table, you will be looking at the composition only of the liquid one, which is also the same as the aqueous phase. And in here, you will see that everything is in the speciated form. Okay, so you will have everything in an ionic form. Of course, there are things that still stay in molecules, but they will dissociate in some cases. For example, you have SO3 minus 2, but you also have the molecule. You have water, but you also have H plus and OH minus down here. So it's all the dissociation of your components that you enter in the streams. So that's the true species, that's the moles true, okay? Now, if you continue scrolling down, then you will see something that is called the molecular apparent for the liquid. This is what I was saying. Nothing is going to be represented in species or in ions. Everything is going to be represented in molecules. The reason why we do this is because, let's say you enter ammonia in your stream and you want to follow the total ammonia all around your process. So it's easier if you use the apparent molecular. Same with HCl, you want to follow what you enter and how it distributes in other streams in your process, okay? And finally, I want to talk about this specific table. This is the MVGs, and MVGs stands for Material Balance Groups. And what this does is, you'll notice that now we have grouped the elements according to their oxidation state. So again, this is another way of tracking your species along in your process. So you want to know how much chloride how much of the chloride that you enter goes to the mixed stream, or how much of the inorganic carbon distributes in your process, things like that. So it's very useful to have this specific way of reporting the data. And I will go through all of this later in the training. But those are the most important tables that we will be using, and I thought it was a very good idea just to show you how to interpret those tables. Okay, so we have created this. One thing I didn't analyze in the report is the pH. Let me go back to the report. So we have that our acid wastes have a pH of minus 0.96, 10 to the minus 3 is a negative pH. The reason why we have a negative pH here is because when we went to define this stream, you'll see that the sulfuric acid is 1 molar. And if you calculate that pH with the normal pH equation, then you will see that you will have negative pH for that stream. Then you have a base pH, a basic pH here for the base waste. And once you mix them together, your pH becomes still acidic. It's 1.1. It hasn't really been neutralized at all. So that's why we're doing the neutralization in this example. Okay. So the next part is that now we're going to start adding our separator unit, and then we will add our neutralizer unit. Okay. So let's save, just in case. And now the second block that we are going to add is going to be this separator. Okay, this is a four phase separator. We're going to click it, we're going to drag it, put it in front of the mixed waste. And the error messages is always going to tell you it needs an inlet and it needs an outlet stream. So this will be the fill stream for our separator. I'm not going to change the name of the separator. I'm going to leave it as SEP1. I'm going to put this name here. And I'm going to click on this mixed waste. Click on this arrow, the blue arrow, then drag it towards the separator until one of these red arrows appear, and then it becomes blue, and then I just release my mouse, and then you will notice that it immediately becomes black, meaning that the connection is successful. And now we are going to add 3 different outlet streams. So we go to the add stream button up here, and we are going to have 3 different outlets. We're going to have a vapor outlet, which goes to the top. And you see that as you put your mouse around this arrow, you will see there is a tag that says vapor, just to make sure that you recognize that there is going to be a vapor only phase. So click on that blue arrow, and then I'm going to put a diagonal here, go. And then click on the white area to release. That will be your vapor phase. The other phase that I'm going to create is the liquid phase. So again, I'll click on this blue arrow, drag my mouse towards the right, click on the white area and release. And the third phase that I want to add here is the solids, just in case I form any solids. And then click in this arrow, drag it. I'm going to put it diagonal so it does that L-shape arrow. Click and then release. Okay. So you have 3 different outputs here. You have a vapor, a liquid, and a solid. And we are going to rename. I'm going to get out of this add stream option. I'm going to hit escape on my keyboard. So now I should be able to see this white pointer. Or you simply go here to the select mode. The software is telling me I have something has changed in my simulation, and that's true. So I'm going to dismiss this because we are adding, actually we have added this separator. Let's rename these streams. This is going to be the SEP vapor. SEP vapor means the vapor that comes from the separator, then SEP liquid, and double click on here to name this SEP solid. Please let me know if I'm not going too fast, or maybe I'm going too slow, so I can speed up. Okay, so that is regarding the separator. And now I don't need to define the streams because they will be calculated, but I need to define how I want to perform this separation. Okay, so I need to click on my separator and go to the properties pane of the separator and tell the software how do I want to do the equilibrium calculation for this separator. It's similar, the calculation type for the separator is similar to those that we saw for the mixer. You'll see that there is adiabatic by default. We have the isothermal, bubble point, dew point, vapor target, isochoric, etc. Pressure specification, similar to the one for the mixer. Then what we are going to do here, you'll see that I'm going to leave the defaults. For this separator, I'm going to leave it as adiabatic, I mean minimum inlet pressure. But you'll see that the separator has something down here. It's called the entrainment. And we are going to click on this gray bar, just to see what are the specifications that we would need to add here. So by default, this separator will always separate 100% of the liquid, 100% of the vapor, 100% of the solids. Okay, but we know that in real life that's not true. Sometimes we will have some suspended solids in this liquid phase, or we will have some liquid in the vapor phase, or some liquid in our solids. So this entrainment option, I got out of it. That entrainment option will allow us to enter that information here. Okay, so if you happen to know how many solids in grams per grams go to the liquid, so you can enter it here. You happen to know how much liquid you have in your vapor, then you enter it here, and things like that. Okay, so how much of the vapor in the liquid in the solid, all of this information. So there are two takeaways from this. The first is that you can do phase entrainment in this. You can definitely do phase entrainment in this separator, so that you can simulate incomplete phase separation. However, that means that if you're doing that entrainment, then you will need to use empirical values. You as the user must know these values and enter these values to run the calculation. The option is there. I wanted to highlight that if you don't have 100% separation, you can always simulate how much of that separation is not possible, and then you come here and enter those values. I'm going to leave it as 100% separation, and I'm going to run this simulation. Save first and run the simulation. Okay. Now that we have added that, then we have added the separator, we can finally add the neutralizer. Okay. And that's going to be very simple, since now we are very familiar how to add unit operations and streams. So the third block that we're going to use is this neutralizer. Same thing, we're going to select it, click on it, drag it towards the place that we want. And we are going to do the following. We are going to connect this separator liquid to the feed here. And we are going to add one outlet that is going to be our neutralized liquid. And then for this neutralizer, we also need to add a reagent as an inlet. So the first thing is I'm going to add this inlet here. So I'm going to click on the top of this neutralizer. And you'll see that as I go down, you'll see a red arrow saying that that is my reagent. And that reagent that we are going to add there is a caustic stream to neutralize the pH of the separator liquid. And we are going to have an outlet. This will be our neutralized liquid. Hit escape, okay, or press escape. I don't know why I say hit, but it's press escape. And we are going to change the names of this. It's going to be a caustic, caustic reagent. Okay. And to the right, we're going to say this is a neutralized. This is our neutralized liquid. I didn't really check the pH of this separator liquid. So what we can do is click on this separator liquid and go to the properties panel to the calculated area and check the pH. So again, pH didn't really change very much from the mixed waste to the separated liquid. Still very low, 1.1. So that means that we will need a lot of this caustic reagent to neutralize this liquid to the desired pH, that is going to be 9. Okay. So the first thing we need to do, the software is saying the neutralizer is not, the pH is not specified, and the caustic reagent, we need to define the caustic reagent. So let's define the caustic reagent stream first. Click on the caustic reagent, go to the properties panel for the caustic reagent, and we are going to change the conditions. Okay, so for this, we are going to change the temperature to 30 degrees C. This is going to be 1 atmosphere. The total flow will be 100. And this is sodium hydroxide. So what we're going to add is water here, 55.51. And the sodium hydroxide will be 1 mole. So this is a 1 molar solution. And we are adding 100 moles of that caustic reagent. Cool. So that is our caustic reagent. Next, we'll see the software is saying we need to specify the neutralizer. We know that we need to specify our unit operation. So what we're going to do here is make sure that we have all our inlets and outlets correctly set up. So we have the feed is the separator liquid, the reagent is the caustic reagent, and my outlet is the neutralized liquid. For the equilibrium calculation, there are two options. So you will have the fixed pH, and then you will have the minimum inlet pressure. There are two options for the calculation type, fixed pH, and the other one is adiabatic. These two options will, at the end of the day, make sure that our neutralized liquid reaches the desired pH that we want, which is going to be 9. But I will not select the adiabatic option. I will select the fixed pH. And pressure specification, let's see how I define it here. Again, it's going to be the minimum inlet pressure, and our pH is going to be 9. We need to define that pH. And now we don't have any errors. Everything is set up. Let's save the file, and now we should be able to run the simulation. Okay. So now that we run the simulation, there is no troubleshooting to do. We can analyze the results. Okay, so we have already gone to the report tab. Maybe if you want to add more streams, so far you have the acid waste, the base waste, and the mixed waste. You can also add all of the other streams if you want, but it becomes a little too much when we want to analyze the results now from this report. It's just so many streams. So you have another way of analyzing the results, and it's using the properties panel, okay? So what we're going to do is we're going to select this caustic reagent here, and you'll see that there is a sub-tab that says calculator. So click on it, and this sub-tab is going to show you two different sections. The stream parameters, again, is what you define, and the calculated, some of the calculated properties. And then you will see the total apparent molecular representation of this stream, okay? So you will see that initially when we define this caustic reagent stream, we told the software, or we gave the software an initial value of 100 moles, but the software is calculating for moles apparent, again, that 242.5 moles of the caustic reagent is needed in order to reach the specified pH, okay? 100 moles weren't enough to increase the pH from a value of 1.13, that was the original pH of the separated liquid to 9. So that means that the software had to add 2.4 times more of that amount in order to reach that neutralized liquid pH of 9, okay? So that's what the software did. Basically, it moved, or it just adjusted this caustic reagent in order to reach the our desired pH. Okay, so with this, we are done with this first example, and as we go through the examples, it will be faster, as we already know how to move around the software. And I'm going just to set up the next case, and we are going to learn how to use controllers and manipulators in our next example. And we will basically use the same, we will continue on the case that we have built so far. And then we will, after this, then we will learn how to do recycles as well. So I will give a 6-minute break. I think this is a perfect time to stop before we continue with our next example. And we will meet here maybe in 7 minutes. So let me just bring this. I like this too. And then let me just put it here. And then we will meet in 7 minutes, okay? Thank you so much for your time. I saw John. John, you had a question regarding your properties window. Was it resolved? I can show you a trick really quickly of how to set up everything back to normal when you lose your properties window.
Yeah, I found that reset button.
Okay, good. And let's see. I don't see any. I don't know if Zeke has any other questions that maybe people have had. Okay. So let me see my list of attendees. Thank you, Hernan. He's raising his hand. I see some hands. Okay. Ying is here. That's good. Perfect. I do see a lot of people connected. And I saw also QD. Hi, QD. Thank you for being here. I see a lot of attendees that I have had the pleasure to work with before. Thank you for that, for being here. And let's go back to our training. So now, as I mentioned before, we have built the mixer and separator and neutralizer. Now I want to basically introduce to you the manipulator tool and the pH controller as well. We will be using at least the first two unit operations that we have built so far, and then we will continue building upon it piece by piece. Okay, so let me just go back to the software. Oops, I opened the one that is not that I needed. And this is what we have so far. Let's save it. And what I'm going to do now is to go to the option File, Save As. Okay. And I'm going to rename this to create a new file. And I am going to say that this is my pH neutralization with manipulator. Oops. Manipulator and controller. So we keep track of what changes we have done in our simulations. Okay, now I need to bring my cheat sheet here just to have it with me so I don't miss any pieces. There it goes. Perfect. Okay, so far we saw that the neutralizer did the trick for us, right? We added a caustic reagent and we told it we want this pH, and the neutralizer simply, as a black box, changed the pH, and we really didn't know what it did. So what we're going to do now is we're going to replace that neutralizer, and we're going to put a controller and a manipulator in order to see what in the background what this neutralizer object is doing. Okay, so we're going to click on this neutralizer and we are going to delete it, and anything that was an outlet stream from that neutralizer was deleted, and anything that was an input or an inlet stream is left, so it doesn't get deleted. Only what comes out of the neutralizer was deleted. And that's okay. We're going to recreate that again. So the next step is that we are going to add a mixer block. So we're going to click on the mixer, and we are going to put it in front of the separator liquid. Okay. And this mixer is going to represent our neutralizer. instead of the block that we had before, we're going to change it as a neutralizer or use it as if it were a neutralizer. So we're going to change the name to neutralizer, just to make sure. And we're going to connect this separator liquid to the mixer. You just run it a little bit to the right and connect it here. In any of these connectors, I'll pick the middle one, blue, release, good. You know what, let me show you another way. If you have issues, maybe sometimes it's very difficult to connect. I don't know, sometimes the software is it's not happy every now and then, so it doesn't really let you connect the streams. So there is another way that you can connect streams, and it's using just if you click on this mixer or neutralizer, you will see here inlets, and there is a drop-down arrow there. So it will identify all the possible inlets. So it knows that there are 4 possible inlets. I want the one that is separator liquid, and it just connects it for you right away. So you don't have to deal with clicking here, clicking there. It's just it just does it for you. Okay. Now we're going to add an outlet stream. Go to the Add Stream button and click on this blue arrow, drag, click on the white area, and we are good. That will be our neutralized. Double click on that name, neutralized liquid. Okay. You can always, if you don't want to double click, you just simply right click on it and use the option rename. That will do the same thing. Okay, so that's the mixer. Now we will have this caustic reagent that is, we are going to use it. But we need to tell the software how much of this caustic reagent we need to add in order to reach a pH of 9 in this neutralized liquid stream. So the first thing that we're going to do is that we are going to add a manipulate or a manipulator block. Again, anytime that you want a manipulator block, not a manipulator block, but any block, you go to the library. So to the left, you will scroll down and you'll see that the manipulator block is this one that is almost at the bottom. It's all the way to the bottom. And it's represented by this square with an M in the middle. That is our manipulator block. So I click on it, drag it. I'm going to put it next to my caustic reagent stream, around here, maybe here, there. And I am going to change the name of this manipulator block. I don't want it to be called mani-1. I want it to be called, this is more like a valve, so we will call it caustic, valve, perfect. And the software is telling me that we need to define an inlet and an outlet for that caustic valve. So of course, we are going to put the caustic reagent as the input for that caustic valve. Okay, so we're going to select the caustic reagent. The arrow part selected, hold the selection, drag it towards the manipulator and drop it or release. Okay, you have your caustic. I'm going to modify this a little, like that. And what this valve is going to do is that if you click on it and we go to the properties panel, what this valve is going to do is that it's going to serve as a multiplier. That's what it's going to do. So whatever factor we tell it here to multiply by, so in this case is 1. So the total amount of this caustic reagent is going to be multiplied by 1, and that will be the exit or the output of that stream that we're going to put in front of this caustic valve. If you put 2, it will be multiplied by 2. If it's 3, it will be multiplied by 3. However, this factor total flow, we will see that our controller will be the one that modify this value. So we're not going to change anything here. We're going to leave the specifications of this caustic valve as total flow, and the factor flow is going to be 1. We're going to add another stream here, and it's going to go out of the manipulator. So we're going to add an outlet for this manipulator, and we are going to rename it adjusted caustic reagent. Okay, because we are going to adjust, this valve is going to adjust my original inlet here for the caustic reagent. That adjusted caustic reagent is going to be the inlet for my neutralizer. And now my neutralizer is way here to the back. So I'm going to just move it a little bit to the right, or I could have just selected this and move it, oops, I didn't do that. And move it to the back, like that. You can play with these configurations. And now we are going to click on this adjusted caustic reagent, and we are going to connect it to my neutralizer. So again, click on this arrow, hold the click, and go to the neutralizer. The blue arrow appears, release. Or you could have just gone to the inlets and select one of the feeds as the adjusted caustic reagent. Okay, so far this is a manipulator. We are manipulating the stream, and we really didn't change anything for the manipulator type. Okay, so let's save. The next step is to add a controller. Okay, and the controller will use this block, okay, to modify the stream depending upon what we tell it to control. So we are going to control the pH. Okay, so we go back to the library and we select the controller. Well, there are actually two types of controllers, and in this example, we are going to use the feedback controller. There is the other one that is the feed forward controller. But for today, we are going to use this feedback controller. It will use basically the information downstream to modify something upstream. That's what that's what it's going to do. So when you bring the controller, it tells you that there are a lot of issues with that because you need to do some connections. Okay, with the controller tool, we no longer need stream connections. What we need is a signal connection. Okay, and what we need to do is select. You'll see that at the top you have the add stream, and next to it there is the add control connection. Click on that. That's the one that we are going to use. So the connection for a controller works in the following manner. We need to go from what we want to measure to the controller, and from the controller to the block or stream that we want to manipulate. Okay, so it's always from what we want to measure to controller to block or a stream. So that's what we're going to do. We're going to start from this stream, the neutralized liquid. We want to measure the pH. So you'll see that there are several connectors here, the red dots. Those are the 3 possible connections that you can do. So I'm going to select the third one. It becomes green when I am ready to do a connection. So click on it, and now drag your mouse towards the controller. And the controller will also show different connector points. I'm going to select this one to the right, click on it. So you have your first connection. Okay, so measured to controller. Controller will read that measurement that you took in here, And now it's going to take that information. So that's our second connection. It's going to take that information. So click on the, once it becomes green, that red button, and go to the manipulator. So the manipulator also has these two red buttons. I'm going to select the one at the top. And once it measures, it goes and tells the valve, add or remove caustic reagent to reach the desired pH. And that is what the neutralizer was doing. Really, the neutralizer was, oh, I'm sorry, I clicked in the wrong place. That's what the neutralizer was doing. The neutralizer was a composition, or it was composed by a mixer, manipulator, and a controller, all in one single block. And this is what it was really doing in the background. Okay, so now the controller. If we click on the controller, we need to specify what we want to do. Okay, what you're going to measure, controller. So let's change the name of this controller. We know that this is going to measure the pH. So let's name the controller as pH controller. And then we're going to click here on the controller, and to the right, there are the target specifications. Okay. We want to measure the target stream as the neutralized. This is going to be the target stream, the neutralized liquid. Now, what type of measurement do I want to do? Do I want to measure the temperature? Do I want to measure pressure, pH, flow, a specific composition, oxidation reduction potential, partial pressures? You can measure any of these things. In our case, we want to measure the pH. So we have selected the pH, and our target value, we already know, that is 9. So we simply enter the value of 9. So one of the warnings went away. We already defined the specification type. But now we need to tell it what we are going to control. So the block, there are two ways of controlling. You can control a block, in this case the manipulator, and you can control a stream directly. In this case, we are using a manipulator. So we select block. And the control block is the caustic valve, as we already named it like that, the caustic valve. And now for the parameter. The parameter will be the factor total flow. It's the only available because in our caustic valve, if you go, the only parameter that we have defined there is the total flow. And immediately you'll see that the factor total flow becomes green, meaning that this will be an initial value, and now my controller is going to change this value in order to reach my desired pH down here in the neutralized liquid. So that is all what you need to do here. There are some options for the controller, okay? So if you want to click on these convergence options, and we will not cover this in detail, but let me just highlight some things from here. These are the convergence options for your controller. In here, you can define the type of method that you want to use for your convergence. You can specify specific tolerance. You can specify the number of iterations for your controller. And you can say, okay, after a certain amount of iterations, please stop. Or after a certain amount of iterations, just continue doing the calculation and see what happens. But in here, we are not going to make any changes. I'm going to leave all the default values. You can always play with this. And if you're interested to know more about this, I can send you information about this, the different techniques and what all of these minimum and maximum values and all of these mean, and I can provide that to you. But at the moment, I'm going to leave the defaults. I'm happy with those defaults. I will save my case, and I will click on the run button to execute this simulation. Okay, so we are good. Everything is fine. It seems that the software didn't have any convergence issues. And what we're going to do is to see if we actually reach the specified conditions. So what we're going to do now is I already showed you the report. I already showed you how to analyze the results using the calculated tab. I haven't showed you a way of also seeing the results directly in the simulation, and that is what we call the callout tables. Okay, so I will show that in this simulation. So what we're going to do here is we're interested to know if we met the specified pH here and how much of the caustic amount of the caustic stream was used. Okay, so what we're going to do is we're going to select the streams that we are interested to know the information, our streams of interest. And once you select on them, you're going to right click on them and select the option, is that 1, 2, 3, the fifth option from top to bottom, and is the add callout table. Okay, you click on the add callout table and it will bring a table here near to your desired stream or the stream that you're studying. And by default, the software will always create a table that shows the temperature, pressure, and pH. Okay, and you can see here that the pH is 8.99997. I will assume that that's 9. I'm happy with that. I don't think that we should be concerned about why it's not exactly 9. Probably it's because we need to go back to the convergence options of the controller and modify if we want a more a tighter tolerance for this number. But it's good. This is almost 9. This is virtually 9. And also notice that there is a change in temperature. The temperature of this neutralized liquid is around 40 degrees C, probably due to heat of reaction, of course, because we are having an acidic solution and we are combining it with a basic solution. So maybe that is what is increasing the temperature here. The second, let me double check that actually, 38, 30. Yeah, so we had a 30 degrees C stream combining with a 38 and the temperature increased. So we are having definitely heat of reaction here. And the other stream that we're interested to know is the adjusted caustic stream. So we're going to do the same thing. We're going to right click on it and select the option add callout. Okay. And I don't like the location of that add callout. I'm going to put it up here where it doesn't cover our simulation. Again, temperature, pressure, and pH. Notice the pH of this caustic stream is 13.7. And unfortunately, this table is not really showing me what I want to see. I want to see how much of the total, or yeah, how much of this of this caustic reagent was added in moles, right? The amount. So how can we add more information to this table? Okay, it's very easy actually. You can either right click on it and select edit, or you can just double click on it. And it will bring a table. And for the ones that are familiar with Studio, it's a similar table to that when you are doing a survey calculation. And this table will have different categories. And I have already explained these categories in the report. Everything here is just summarized in different categories. So we will have the stream parameters, phase flows, phase fractions, thermodynamic properties, the apparent and the true speciated information, the material balance groups, scaling tendencies, etc. What we want to know from this table is to know the total moles that were required to neutralize the stream. So we're going to go to stream parameters, the first option up here. Click on the plus sign here to expand this. And then we are going to select the option moles apparent. I want to know how much of these moles were added in order to reach neutralization. So you have two options. You can double click to add this variable as a selected variable, or you can just click on the right button to put the moles apparent in your selected variable screen. So once you're done with this, we're not going to add more. I just don't want to know any more information at the moment. And I'm happy with this, so then I click OK. You can always go back to add more if you need. Just double click and add more information. For this case, okay, so notice that now the software is saying that 242 moles of this caustic reagent were needed in order to reach this neutralization. And if you remember in the previous example when we used the neutralizer, this was exactly the same amount that we needed for the caustic reagent. So initially, for this initial caustic reagent, we said that we had 100 moles. The controller manipulated this valve, and now the total amount of moles that I need of that caustic reagent is 2.4 times that amount, 242.5 moles per hour of that specific stream. Okay, so that's what the software did with the manipulator and the controller. This again is replicating what the neutralizer was doing, and it's also introducing to you how to use controllers and manipulators. Before I jump to the next example, I want to show you something really quickly about the results of this output down here. So we don't have any errors, but we can always check the output. And this output window is going to tell you what did the software do for your calculation. And for the ones that are interested to know how the software calculated this is where you go and read this output window in order to see what the software did, okay? So let me see if I am missing something here. Yeah, no, this is what the software did. So what the software did first, if you scroll all the way up this output window, is that the software has generated your chemistry model here, okay? Identified all of the input streams, the base waves, the acid waves, the caustic reagent. Then it realized which blocks were part of the simulation and the order that the software is going to use to solve every single one of these blocks. So first was the mixer, then the separate, then the manipulator, then the other mixer, and lastly the controller. So with the controller, now this is everything related to the controller. The controller has a target of a pH of 9. Initially computed a pH of 2, okay, where it started with a value of 1. Then it revised that value, it increased that value, and then it says, okay, it didn't converge. And that's right, because the pH of 2 is far away from 9. So that's not a good, that's not a solution. So it goes back, increases the parameter value to 1.01, revises the pH, still not good, and it continues doing that until you'll see that it computes a new pH, the target is 9, still not good, this is the third iteration, it doesn't converge, until it finds the caustic value of 2.42 down here. It computes a pH of 8999 and the target was 9. So it says, okay, this is pretty good, it's enough. So now the controller has converged. So that's all what it means. This is all of these numbers that you see here. That's what it means that the software is doing. It's telling you exactly the steps it took in order to converge the controller and, of course, the simulation. Regarding the convergence monitor, it will be just a graphical representation of what I just showed you, and it will tell you how many iterations it took. In this case, was a total of 9 iterations in order to reach convergence. Okay, so with this, it ends the part of the controllers and manipulators. I'm going to let's save this example, because now we are going to go to our next topic, that is going to be recycles. Okay, so let's save this. Any questions at the moment? Let me see, I have some questions here. Solid lines. Give me 30 seconds here and I'm going to see. Okay. There is a person that says that it does not show that it's not seeing the convergence monitor tab. How can I get to see it? Yes, so if you're not seeing this convergence monitor tab, it's probably because maybe it got closed. So what we're going to do is we're going to go to View, Windows and Toolbars, and make sure that you have selected the option Convergence Monitor. That should help you to bring back that Convergence Monitor. There is a comment from somebody says here, it says solid lines are for streams that carry components and properties, dashed lines are for logic connections. That's correct. So we will have the streams, all of these solid lines are carrying mass, and anything that is dashed line is carrying signals, control signals. And so it's basically measurements. Imagine this as when you have a probe in a pipeline measuring something, and that will trigger a signal to a valve, and that's what this is carrying for your simulation. Okay, I think that that's good. Only the you see. Okay. Okay. Gary is saying that still does not show up the convergence monitor. I wonder. The convergence monitor, make sure that you have 4 tabs. You're clicking on that one. I don't know what else could be causing that the convergence monitor is not showing. We will need to see your case and see how your screen is showing. Okay, maybe at the end of the class, because I only have 30 minutes left to explain recycles, maybe at the end of the class, Gary, we can see what happened to your convergence monitor. Sorry about that. Okay, so let's move to our next example. We're going to talk about recycles. Okay, so far we learned how to set up a manipulator, a controller, and now we're going to see how we set up these recycle streams. Okay, so frequently a process recycles part of a stream and puts it back to a process. There are many reasons why we want to include these recycle streams. Sometimes we want to minimize waste. Sometimes we want to increase residence time or increase the purification of a product. Okay. So what we're going to do here is that we're going to add to the previous case that we just saw a new mix block. And then we will also add a splitter block. And we will be adding sodium chloride to remove some of the solids from the solution. And then here we will be adding the salt, sodium chloride. And then what we're going to do is some of those solids will go back to the upstream of to an upstream unit, and some of them will be just purged. Okay. So let's go back to the simulation. And this one was the one. Okay, so let's go back to simulation. Let's save this one. Okay, and now we are going to go to File, Save As, and we're going to change this name. Okay, we are going to name it as pH neutralization with recycles. We're going to override the name, and we're going to continue building upon. We're going to continue building on this case. Okay. Okay, so now, the first thing again is units. When we're working on a case, we want to make sure that all the units are fine. We already know that the units are correct because we have been working on this case. The second step is to make sure that we have defined the chemistry. And as I showed before, we are going to add salts or a salt in this process. So that means that we need to update our chemistry. So let's click on this chemistry tab, and we are going to add our salt, sodium chloride, NaCl, enter, and that has updated our chemistry. Okay. Let's dismiss this error message. We know that we have changed the simulation, so click dismiss, and they go back to the flow sheet tab, or click on the flow sheet tab to go back to your process. I'm going to move the simulation to the right, so I'm going to use this scroll, this bar down here. I'm going to move it to the right, because I'm going to add 2 more blocks in here. The first one is going to be a mixer. I'm going to scroll up, select mixer, drag it, put it to the right of this neutralized liquid, and I'm going to connect the neutralized liquid stream to that mixer. Okay? I am going to change this name for this mixer. I don't want it to be called mixer 2. I want to rename it salter. Okay, so that is the name, salter. Then we are going to add, for this specific example, we are going to add an input stream, and we are going to also add an output stream. So we go to the add stream, and we're going to add an outlet. Click here, drag it to the right, add my outlet stream. I'm going to move this neutralized liquid up here, this table. I'm going to add a second stream that is going to be my salt. I'm going to click on this white area and go to one of these red arrows, click on it. I want to rename this stream. It's going to be NaCl, so we're going to put it salt. And I'm going to move that name to the left. Then to the right, this one is going to be named as our salted stream, okay? Because we have added some salt, because we want to precipitate some solids. We want to saturate this solution to cause precipitation of solids. Okay, so there are 2 things that we need to do here. First, we need to define, if we go to the error messages here, it says that we need to define our salt stream. And it's saying, okay, please let us know how much of that salt you're adding and the composition. So for that, we are going to say, and let me bring my cheat sheet I always like to have here so I know that I am doing the right specifications. So for the salt stream, I am going to add 75% moles, 75 moles per hour, not 75%. So 75 moles per hour of salt, of NaCl. So we're going to enter 75, okay? And already my total flow is calculated. The conditions of this salt is temperature and pressure, 25 degrees C and 1 atmosphere. Okay. One thing that I want to mention here, and is that this is only a solid phase. So I'm going to tell the software that the phase of this stream is solid only. So by default, in these advanced options to the right, you see that the software defines the set phase as no special condition. It says, don't do anything, assume that it has all possible phases in your stream. But we know that this is not the case. In this case, we don't have any water, any vapor. We know that it's only a solid. So we go to the option set phase. You see that there are a lot of options. You can define if it's a liquid 1 and solid only, vapor only, no vapor, liquid 2, etc. For this example, it's a solid only, and that's what we're going to tell the software. Select the option solid only. And what this does is that it will help us, or it will reduce the calculation time, since the other phases will not be included for calculations. So it will be only solid phase, and that's it. It doesn't need to calculate aqueous properties, vapor, nothing of those equilibriums will be considered. Okay. The next step is to set up this salter. So for that salter, we know that this salter will operate at isothermal conditions. So we're going to click on it. We are going to go to the equilibrium calculation and change the calculation type from adiabatic to isothermal. Okay. So for that isothermal, then I have to define the temperature, and that temperature is going to be 40 degrees C. So we'll enter 40, and the minimum inlet pressure will be the pressure specification. That's it. So at the moment, this is all what we did. We are going to save the file, and we can run the simulation. Okay. So we still have our pH on the neutralized liquid at 9, everything, nothing has really changed. What we need to know is if this salt stream is having some solids precipitating out. So you will see to your right, if you click on the salt stream and you go to your properties panel, then you'll see that in fact the software is calculating the prediction of a solid phase. So you have some aqueous phase and some solid phase here. And if you want to know which solid phase is being formed, then we go to the View Detailed Report down here. And you can always go and in here and see what specific solid was formed. So if you scroll down, if you go to the solids here, so you'll see in the composition through speciated, you see that the sodium chloride 10 moles of halide of sodium chloride, 10.44 moles per hour, are being formed in that stream. Okay, so you specifically know which solids are being formed. Okay, so we go back to the flow sheet. We have one more piece of information here to add. The next one, I'm going to move this to my right with this. I forgot the name of this. The scroll bar. Down here, we are going to move it to the right. And we are going to add our next step or our next unit operation, that is a splitter. And actually, we haven't worked with a splitter so far. So that will be good because we will learn how to set it up. So we will go to the library and we will try to find our splitter. Okay. And there is our splitter is down here next below our mixer, or at least in my screen is below the mixer. Maybe you have it in a different place if you have moved this window. And then we will just click on it and put it to the right of my simulation here, just to the right of this salted stream. Notice that there is also a component splitter. I will not use this component splitter today, but I just want to highlight the differences. The splitter splits total flows. So if you have 100 moles, you can tell the splitter to send 50 moles in one side, 50 moles to the other one. While the component splitter actually selects a specific component, and that is what it splits. It's, let's say you have sodium chloride and water, and you can tell the component splitter to only send sodium chloride in one of the streams. Okay, so that's the difference. For this splitter, we're going to connect this salted stream to the feed of this splitter. And now we are going to add 2 output streams. Okay, so we click on the Add Stream button, come here to the first outlet, click on the blue arrow, drag to the right, click on the white area, and the second outlet will be down here. we're going to click on the blue arrow, drag it to the right, click on the white area. And I'm going to press the escape button to get out of the adding streams. Now I'm in the selection mode. And I'm going to rename these two streams here. I'm going to rename them. This one is going to be purge. We're going to send this to waste, or maybe it's some treatment, purge. And we are going to rename this one down here as the recycle stream. This is what we're going to recycle. Please save, just in case, you never know. And now what we're going to do, well, let me just show you something here. We see that our process is getting longer and longer. So I like to use this zoom to fit button up here that I am highlighting, this one. That is represented with four different arrows going up and down to the left and right. So if you click on that button, it will basically put everything back, or all your process will be shown in the flow sheet area, and I like that. So sometimes what you can do if you want to make it look bigger is to make sure that your streams are shorter, or you just move some of these objects to the left, right? So you have more space, and then you can maximize this so it's more clear to see what's going on. Okay, just wanted to highlight this zoom to fit button. Okay, the software still is telling us you need to specify your splitter. That's right, we haven't specified it. So for the splitter, again, it's the same, similar to a mixer. You have your inlets, your outlets. However, in the parameters section, you will see that there is an option that says outlet split. And you will see an option that says edit. Okay, so we need to click there because that will take us to a new window. Okay, where we need to specify the fraction that you want to purge and the fraction that you want to recycle. You can do it either in moles, mass, volume, fraction, or flow. So if you have a specific flow in mind, that you always think that you're recycling a specific flow, you can define the flow. Or if you want to say 70% goes as a recycle and 30% goes as a purge, you also have that option. So for this case, we're going to select moles because we have been working in moles. And we're going to enter the fractions. So we are going to say that 25% of the salted stream goes to purge, and 75% of that, or 75%, which is the rest, goes as recycle. Okay. So again, let me show you how I did this. You select the splitter. You go to the parameter section, you click the edit button. We have selected the moles option here for the flow basis, and we are entering or defining the fractions, how we want to split. 25% goes to purge, 75% goes as recycle. And then we click OK to accept the changes, save, and run the simulation. Okay, so we are almost done here with this example. Okay, so we have calculated the properties of the purge stream, the recycle stream, etc. But our original idea was that we are going to recycle as part of this splitter or this salted stream. We were going to recycle back here to this mixer upstream of this process. Okay, so what we're going to do is we're going to select this recycle stream, again, this arrow here, and you'll see, and you just click on it, drag it, and we're going to take that recycle stream to our mixer. mixer 1, and we're going to select any of these red arrows, maybe the one in the middle, and it connects my recycle stream. If we don't want to do it that way because it's too complicated, maybe it's just not something easy to do. So we click on the mixer object, and we go to the inlets of that mixer, and we are going to select the option recycle. Perfect. So it connected the stream for us. Now this looks a little bit messy. I really don't like how this recycle stream appears here. So we can rearrange this. Simply we need to take one of these anchors by the streams and just click on it and drag it down. I want to put it down and maybe a little bit to the left, just because I want it to look more cleaner so we understand what's going on. Oops, it just didn't like it. Let's put it back again. Let's rearrange this. Looks cleaner. Okay, I'm happy with this. Looks much better to understand that there's a recycle stream. And let me zoom to fit so we see everything in the screen. And now we'll see that we cannot run the simulation as it is. This recycle stream requires some additional information prior to running the simulation. In processes, when we have a process without any recycle stream, the order of the calculation goes from left to right, right? So it will calculate first our mixer, the separator, the neutralizer, etc. But when we have a recycle stream, we need to tell the software how to calculate, or what is the order for this calculation, okay? So you will see down here that the software has a warning saying that we need to set a third stream. And the third stream will help us to divide this recycle stream, and basically we're going to split it in two, and then the software can go ahead and calculate the normal and perform the calculations in the normal order. But if we don't do that, the software doesn't know from where to start. It's from the splitter, and then goes to the mixer, and it just gets confused. So it needs to be, the split needs to be split. The recycle needs to be split or paired, and that's what the software is telling us here. So if you click on this error message, it says click here to set up paired streams. And if you click on there, the software will show you that in fact we are having a recycle stream here. Okay, we are having a recycle loop. And to the left, the software is saying that it suggests the following streams: the recycle, mixed waste, sep liquid, neutralized liquid, or the salted stream as the possible third streams. And it just makes sense that the recycle stream is going to be our third stream. So we're going to click the recycle stream. You'll see that immediately the software has put these two lines, or this double diagonal mark on that stream, saying that we have selected that stream as a third stream. So we click OK to accept the changes. Okay. And now in here, you'll see that the software again put these double lines here. You could have just simply right-click on the stream and select the option Set Third Stream. You could have done that as well. That's the other option. And notice that the software has put some initial values or initial guesses for this recycle stream. Okay, it really took the values that we calculated for this stream and put them as initial values to use them for this first calculation in the mixer. Okay, so with this, we have already completed the recycle here. We don't have any error messages here. We can go ahead and save this file, and we can go ahead and run the simulation. Usually with recycle streams, the software takes a little while to calculate or to reach convergence, but this is a very easy example. We already give very good initial values for this third stream. So the software calculated super quickly the results for this specific simulation. So now that we are done, there are no more errors, no troubleshoot. Now we can analyze the results, okay? And to analyze the result, we already have these call-out tables here for our adjusted caustic reagent that should be around here. I don't know really where to put these tables. Maybe let's put them down here, one next to the other one. And let's analyze what happened. So the neutralized liquid pH still is 9, so nothing has changed there. But the moles apparent for this caustic reagent, the adjusted caustic reagent, now has decreased. Initially, if you remember, we had that it was 245 moles per hour, and now this total moles apparent has decreased to 222 moles per hour, okay? And the reason is because maybe some of the unreacted caustic that we had in this neutralized liquid, and then it went back here, and now we are reusing it. So we don't need to use as much of this original caustic reagent because we are reusing what it didn't react after we have added, after we did the neutralized liquid here, right? Hope it makes sense. So we added caustic reagent, maybe all of it didn't react. We are recirculating some part of it, so we are reusing it, and hence we don't need as much caustic reagent as we did before, because there was some of it present in the process, so it will decrease the total amount of fresh caustic reagent that we need for the process. Okay. So that was for the recycle stream. Let me see if I am missing something. Okay, so again, if you go, there are no errors. Your output file, if you analyze what the software did for your simulation, chemistry model, it was doing all the controller here for all the calculations here for your controller. It took several iterations for the controller, and then it needed to do the recycle stream as well. Okay, and let me see. It's a long calculation because it needs to converge the recycle stream and the controller. So maybe it's easier if we go to the convergence monitor. So in here we will have, this is how many iterations it took for the controller to converge. And if I select the recycle, this is how many iterations it took for the recycle to converge. Okay. And because we are having this recycle here, initially we split it, and this is going to give us different results. So it's going to interfere with the controller calculations, and that's the reason why we see much more iterations for the controller in this simulation. Okay, so that is what I have for today. It seems that we have 7 minutes left. 7 minutes left. So I will take any questions, and then I will leave it here so that we can continue next class with our next example.
And then can we show the setup again? We have one user whose controller didn't converge.
The controller setup? The controller?
Yes,
setup?
please.
Okay, sure. Let me see. It didn't converge. The controller didn't converge. Oh,
No.
so let me see. For some reason, I can't see the chat. So I can't see the exact question. Chat, there it goes. The control refer to conversion the maximum iterations of 20K. Okay, so for the pH controller, what we did here, and then what we're going to do is we have selected the neutralized liquid, we have the specification as pH and the target value as 9. I had the block caustic valve factor total flow. And then for that, maybe the caustic valve needs to be manipulation type total flow. I will need to see your screen to see why it's not converging. Maybe there is something that we are missing and I don't know what it is. So maybe if you stay or you share your screen right now, maybe we can help you with that. There is another question here. Did you ask the second? Oh, for the second report, it was simple. I was simply trying to understand this. I think it was the salted stream. Yeah, the salted stream. So if you go to, you click on the salted stream and you go to the view detail report, that will create this second report here for you. Okay. And so I will ask the person that was having the problem with the controller, if you don't mind sharing your screen, we can give you sharing privileges, and then we can see why the controller is not converging. So that will be good.
Yeah, give more. Do you want to do that now, or do you want to stay afterwards and get help?
I think I can stay.
Okay, that's fine. I think, Diana, we had one more question about how to anchor some of the windows in different places. We had Mohammed was asking us about keeping this. Let's see, where is this question? Docket on the right side of the window, the properties window. I don't know if Mohammed, you still have this question.
You mean like that, like auto hide? I mean, you can modify this as you prefer. There is one way. The first one is you can hide the auto. You can simply, you'll see that there is a pin icon here. You click on it, that will hide your properties window. And if you need it, you simply hover over these properties or watch tabs that you see to the right. But if you want it back, you simply click on the pin and it will pin it to the right. Now let's say you don't want your properties panel to the right, you want it maybe to the left. So you can simply click on this blue area and drag it. And you'll see that there are several, there is some help here in the window. There is like this cross here, or there is to the right, also this icon here. It's telling you that you can drop that window here or to the left. So if you want to put it to the left, you just simply click on this icon and it will put your property window in the left, if that's how you prefer it. If you don't want it there, so again, you just auto hide it and it goes to the left. If you want it back, you pin it. But if you want it back to your right, you drag it and use this icon to the right, so it will put it there. Okay, I hope that answered the question. You can always play with these windows. I have been keeping the windows, the windows that the software comes with by default, so I don't create confusion. But you can always change the windows size, the windows location, anything you want. The software allows for that. Okay, so I think that there are two people that need help, so maybe yeah, they can stay after noon.
Sure. Yeah, let's do that. So, everyone, thank you very much for your time today and your participation in this class. You know, we have a lot of folks in the in the attendee list, so we may even have some more on Wednesday. So, in the meantime, before Wednesday's session, which will start 9 a.m. Eastern again, like today, please, have a play around with the software, look at some of the cases, bring some specific questions. We will have time on Wednesday's session to address any outstanding issues or questions about how to navigate, how to add streams, how to view results. And Wednesday we'll get a few more examples. So today was a lot about setting up, how to use the software, how to navigate, where to look for information. But we're here in the meantime if you have something that you'd want to address prior to getting back to the group. But otherwise, for those folks who need to stay and have questions answered, please stay. For the rest of you, again, thank you so much, and we look forward to seeing you on Wednesday.
Thank you for your time.
Diana, I have a question if you have a couple minutes.
Yeah. Please stay. The ones that have questions.
Yes, at the beginning, the very first sample, you showed to use a splitter. Not splitter. What was it? Equalizer. Instead of using the manipulator and the controller. So is it a better way to do that, or you would rather recommend to use the manipulator and the controller?
Yeah, I will highly recommend to use manipulator and controller rather than the neutralizer. The neutralizer usually not always converges because it doesn't allow you to manipulate as much as the manipulator does. And sometimes you cannot track the error. Why is it failing? So with the manipulator and with the controller, it's easier to see where the simulation failed, either in the controller or the manipulator, so you can always fix for that.
Okay.
Yeah, usually we prefer to use manipulator or controller over the neutralizer. When the calculations are not as complicated, the neutralizer is okay. Because sometimes you don't want so many things, right? You want a black box covering the manipulator and controller so people understand what you're doing. But if the calculation sometimes is complicated, it's better to do manipulator and controller.
Okay, thank you.
No problem, Ian. Okay, we had also a question for why the simulation wasn't converging for the controller. I think the person is here, right?
Yeah, Gilmore. Gilmore's here.
Yeah, sure. I can share my screen here.
Yeah. You should see in your screen an option that says share.
I'm going to make you presenter, Gilmore. That way you can.
Mm-hmm.
Sure. Let me know when you can see my screen.
Sure, yeah. Okay, so let's see what's going on. Click on the pH on the controller, please, in the pH controller. And see. If you could please click on your pH controller.
Sure.
Right, pH plug factor. Okay, that's good. The controller is in the maximum iteration, pH controller. And now click on the caustic valve, please. pH 13, yeah, that's good. And good. And now click on the caustic reagent stream, please. Next to the manipulator, yeah. 55, 1 mole. Okay, that's correct. Close. So, okay, I wonder why it's not. Okay, so now go back to the controller, the pH controller. And let's go to convergence options. All the way to the right in your properties panel, and then just click on convergence option.
I need to undo.
Yeah, You were right, in properties. So go all the way down in your properties panel, and it says convergence options. And just simply change those the maximum iterations to maybe 50. And then the no converged rule, change it to continue. Oops, you got
Yeah,
it.
I almost.
So convergence options, I wonder why they push. Okay, and then change the not converged rule to continue. Okay, and rerun.
Hey, Gitmore, did you get version 10 installed? Or are you still
Yeah.
on? Nice. Okay.
I have 10.
Okay, great.
Nope, I don't understand. Okay, so it says total flow mole. Okay, so click OK. So maybe for the caustic reagent, click OK. Go to the caustic reagent and put a value of, yeah, click on caustic reagent, and instead of the total flow in moles per hour, put one mole per hour.
Okay. Yeah, it could be some of these, base acid numbers which I might have missed, but
Yeah, could be. Click run. No, still a problem. Okay, so one last thing. What we're going to do is just disconnect the recycle stream first. Disconnect it. Maybe it does have a bad in yeah. Now rerun. Okay. Now connect the recycle again. And rerun. And if not, then we will need to see your file. Oh, yeah, sorry. You need to set the data stream. Okay, click OK. And right click on the recycle stream and set as data stream and rerun. We will need to see your case. Yeah, we will need to compare the basic acid waste and all of that and see what's happening.
okay.
Is it possible that you send us this file? I will put my email here, Diana.Miller at olisystems.com. Or you can send it to oli.support at olisystems.com.
Sure.
Okay.
So I just send like as it is, right? Like save and send this file.
Yeah, just save it as, send it as the pH neutralizer with recycle, and just send it to me.
Okay, sure. Thank you.
Yeah, no, sorry, I don't understand what could cause this.
Sure.
Thanks, Skip. We'll get back to you soon.
Diana, are you still there?
We are still here.
Yes, I have a question. By accident, I kind of moved the navigator, make it float maybe. I try to dock it back to the original top left corner. I just cannot make it back. I can make it back to the right, but it's always kind of alternating with library, can only show one.
Do
Then
you want to share your screen?
yes. Where? Yeah, share. Let me see.
Does you need present?
Not yet. Not yet. You cannot see, right?
Not yet. No, that's presenter. Presenter, right? Okay.
Can you see it now?
Yes.
See. Now everything is all messed up.
Okay, it's okay. That's easy. I will show you a very easy way that you don't have to do this anymore. So just show me just close all of this, all the flow sheets. Just save them and close them.
Save it. Okay.
And close.
Save it and close the whole flow sheet.
Yeah, close the whole flow sheet and go to your desktop.
Okay. Where is the?
Yeah, go to your desktop. Wherever
I do not have it on the desktop. Let's see.
Wherever you have your icon.
Training.
Wherever you have your flow sheet icon. No.
Not this one?
No.
Okay. Just open the flow sheet from the beginning.
Go to your desktop wherever you have your icon for flow sheet.
I do not have it on the on the desktop. Oh yes, it is there.
Okay, so what you're going to do is press the shift button. Press the shift button the whole time. Keep it pressed.
Okay.
All the time. Do not release it. And double click on the icon of flow sheet. And keep the whole time the shift button pressed. And
sorry, I cannot hear you clearly. Can you say hold the shift?
Hold the whole time, and then double click on the icon of flow sheet. And keep the shift button all the time pressed until flow sheet opens.
So I need to click on the flow sheet icon as well then?
Yeah. The whole time keep shift button pressed. That is normal.
So when I open a new one, like the one that I have, just let's see.
Just open it from here.
Close this one then.
Yeah. It should go back to normal. Oh, I didn't.
No.
It should.
All instances need to be closed.
Yeah.
All
the cases.
Yeah, you should have closed.
Do I need to reopen it?
You need to close everything. And all the flow sheets, all the flow sheets. No flow sheet open at all.
Yeah.
And then redo the shift. And open from here. So file.
Open from here. So I cannot go to the original file, just need to open from here then.
Oh, you should be able to go to your.
Let me see. If I open from here, it seems okay. Okay, just in that case, I need to save this one.
Yeah, just save it and it will keep.
Then it will be, okay. In this case, it should be everything back to normal.
Yeah, everything should be back.
Okay, thank you. By the way, where is the raise your hand button? I cannot find it.
The reset button, I think, is in tools.
Where?
How to raise your hand. That's interesting, Ying. I didn't see it either on my part. I thought if you go to yours, can you click on your name in the?
Oh, I thought that the reset button in the flow sheet.
Pressing the raise your hand button. If you go, can you see the participants panel, Ying, on the right side, maybe?
Yes, the meeting. There is that meeting thing. I cannot find it's just shrinking to small windows. I cannot.
Okay. Yeah, there should be under participants. I think you can click on yourself, and then I think you should be able to raise your hand. I'm not seeing it show up for me, honestly. That's how
I cannot. I find myself, but I cannot click. I clicked, but let's see.
Yeah.
Click on myself. But it's not here. I do not see the whole meeting window anymore. So I do not
Everything.
Yeah, if you stop sharing, you might have a better.
okay. Stop sharing.
Yeah.
Stop.
See, we will sort this out. Before,
Stop sharing.
Yeah.
Okay, now I see. So if I look at the click on myself. No, I still do not have it.
Well, yeah, I don't see it on me either. So let me.
That's what I heard during somebody else does not have the hands. So it's okay. Next time, if I have to do it.
Because I did see people raising their hands, so it must be there, but who knows where.
Yeah. Yeah, so at the beginning, Jordan shared some slides. So those slides are very helpful for the overall understanding. Will you share that set of slides as well, not only the training one?
Yes, we can package those all together. That's easy enough.
Okay, that sounds good. Thank you so much.
All right, thank you.
Thank you. Have a nice
Okay, have a good day.
Wednesday.
Bye-bye.
Bye.